Ashwan, Kanchit Devan, Kanishk, I could find 2 Jagger. Please log in with 1 device. Infinix, Jayashri, who is that Infinix? Harshada, Kanish, join with your school code. Who is that Infinix? Please log out and come with your name. Who is that Oppo? Oppo, please log out and come with your name. Sana, Satish Kumar, Shridesh, Shreya Saditya, Yogalashmi, Vivo. Come with your name, ma. Not West, Vivo. Please rejoin. Leave the session, rejoin us. Your name. Tapasvi, your school code has been given in the WhatsApp group.
Good evening, sir.
And then come back. Vinit Krishna, please come with your school code. It's given in the WhatsApp group. School code, your name, and then school name. Good evening, sir. Sudharani here, sir. So you're not audible, sir.
So good evening.
Do all of you?
Yeah. Yes, sir.
Okay.
Audible now, audible, sir.
Okay, right. So when do we start?
We'll start, sir. We'll start by
6 o'clock, eh?
6 o'clock. Yes, sir.
Still time is there. 5 minutes.
Yes. Good evening, sir. Vivo Xiaomi, this is a last call for you to change the name. Otherwise, you'll be removed from the session. Vivo 1906, Xiaomi, and Oppo. This is a last call that you come with your name. Otherwise, we'll not be putting you in any attendance for you. And we don't know who to put. So please rejoin. Otherwise, you'll be removed from the session. Coordinators, if you know, please ask your students to change. Kapilan?
Good evening, sir. Sir, good evening, sir.
Kapilan,
Yes, ma'am.
we shall start the live. Make ready for live.
Yes, okay, ma'am. It's
We'll
all
start
okay, ma'am.
shortly by 6. There is there. Good evening, sir. Shall we start, sir? Please welcome, sir.
Hello, so shall we start?
Yes, sir. Please, sir.
Students are there, 161 participants. Okay. Let me
Good
share
evening,
my
sir.
slides.
Yes, sir.
Good evening, sir.
Good evening, good evening. Why you are attending these classes? This is for students. You already last time you have gone through. It's not for elders, it's for students. Okay, so students, good evening to all of you. We have seen last time about the space, universe, and then black hole, so many things we have seen. Today we are going to discuss about the evolution of rocketry and the basic principle of rocket. So you see that in the olden days, many years before, in Alexandria, the one hero, one person, their name is not known. He developed similarly a rocket type device called Aelipile. This is in 100 BC. So what he has done, he has made a tank like this, put water inside, and flame. He put the fire beneath, so that means water becomes a steam. He has got a rolling device with the two holes opposite, and the steam goes inside, and they are let out through this. So it starts rotating. So these people were it's a like people show circus on the road. Similar thing he was showing on the road, and then people were enjoying. Hey, it's very interesting to see the whole thing going. But nobody knew at that time the principle of rocket. But this is one of the things which is started very early. The device used the principle of action and reaction. Then many years afterwards, during the 13th century, the Chinese, they found a chemical. This chemical is a mixture of potassium nitrate, sulfur, and charcoal. So this has given big fire. So they started using it, and they packed inside a bamboo tube attached to a long stick, and then attached with the arrows. You can see the arrows. So they did that, and they fought the war with the Mongols in 1232, and they were very successful in deploying these. Let me delete this. Very successful in showing the thing moving fast, the arrows moving fast. Then one interesting thing happened. One rich man, he started sitting on a chair, and bottom you put a number of rockets like this. These all they like the same thing, like the fire arrows. You put that. One who attempted to use rocket power to launch himself into space. He said that you fire that, and there are 47 rockets he put. They fired the rockets, and it flew. The whole thing, he went up, but he didn't return. Where he went, nobody knows. No one knows where and who went. So this is the interesting episode which has happened. Again, the rocket principle. But as I told you last time, the principle of rocket properly used by Tipu's men in 1792 war.
The British found new metal rockets for the first time at the Battle of Pillai in 1780. Tipu's rocket set fire to a British ammunition pond, which contributed to the defeat and surrender of the British brigade.
So this rocket is like this. This 2 kilogram gunpowder, the same gunpowder what Chinese used, and there's a nozzle and igniter, and they attached a sword to that. We have seen that number of rockets going up, swirling, and this sword is heavier. There's no control, so they were tumbling and piercing the horses which came. The British came in horses, so the horses were hit by these rockets, and the people ran away. So these rockets are stored in Woolwich Artillery Museum, and they have written with golden letters that it was used by India in 1792 war, and the British were defeated. You've seen the video of the British video. There you heard that the last few words you hear.
To a British ammunition column, which contributed to the defeat and surrender of the British brigade.
So British, he says, defeat and surrender of the British. So the British acknowledges that India has made these metal rockets and the first time and used in war. So this is the type of thing they made. They made a launcher type of thing. You see that the whole advanced technology they used at that time and put this tube, this a canister launch, which we are trying to use now. But they see that the fellows, they used long back and they fired it. So this rocket technology went to British after 1799, and the one Colonel William Congreve, he took away 10,000 of these rockets and started analyzing it, and he increased its range from 1.5 to 3 kilometers, made it a bigger rocket. And this he used it against the British in the military against Napoleon in the Waterloo War, and Napoleon was defeated. Then they used in the Henry Fort in 1812 against the Americans. So our rocket technology went to America, went to Europe, and that was the early stage. Then in the recent times, in the 19th century, one person came, that is Dishevelsky, is a Soviet Union Russian, a man who could not hear. He was a deaf man. He was not admitted in school because he was deaf. He was standing outside the window and seeing what that the teacher was writing. His mother taught him, and then he became the teacher of the same school. And then he started thinking about the universe, space, and also the rocketry. So his theory was that human will get out of their cradle. Earth is our cradle. Like a child gets out of its cradle to walk, to go out. When it grows after 1 year or 2 years, the human race will get out of Earth and will go to new planet. This is his theory, and he has talked about human will be settling in Mars first, and then they will go beyond the solar system. So these are the visionary statements he has made. And at that time rocket was not known, but he talked about rockets. But the real rocket was made by Goddard. Robert Goddard is American. He made a rocket. You can see the rocket. It is a small rocket like this. This is a rocket motor, small rocket motor. And you got the fuel and oxidizer. And the fuel and oxidizer, they are pumped to the combustion chamber. This is the combustion chamber. And this is the nozzle. This is a liquid propellant. So because of this, the two go and join there, he needs igniter because the type of work, type of the fuel he used was this oxygen and liquid oxygen and gasoline. So that needed an igniter. If it is storable propellant which we are using, they are called hypergolic. They will ignite themselves. But at that time, what you used was different. So that needed an igniter. So once the ignition takes place, the whole thing was coming out. It's like this. You can see that fuel, oxidizer, they are in different tanks. So there's a pipeline, there's a turbine, which pumps it in a particular rate. Similarly, both are coming. And once they come together, then the combustion takes place. This is the combustion. And then the exhaust is diverged. When you diverge, you know what happens? Velocity increases. So that is why they want to have a divergent system. So push it. You have to push it. So this action and this reaction is pushing it. Then he started developing a really bigger rocket. You can see the bigger rocket what he made. So that was the thing he did. He is the real contributor of a rocket in those days. That is 1926. Then 1942, a big group came from Germany with Oberth leading and von Braun sitting with him. They are the disciples of Oberth. They made a bigger rocket, very big rocket called V2. This also again using the spirit they used as the oxidizer. So this is a very interesting thing. They have used different types of fuel and oxidizer and made this rocket, which is a very first guided missile. So they have made the guidance, everything they made. So the Hitler said that this should be used in the Second World War. So they had to produce 5,000 of these rockets, and they fired against the British, against the English Canal. The whole thing was launched. So this is a very interesting rocket which they have made. This is the first big team, and in Germany, which has made a big breakthrough. But during the Second World War, later, the British and Americans, all these people, they destroyed the whole place where this rocket was developed and took them as prisoners. The von Braun was taken as a prisoner to America, and the job given to him was to develop rocket for America. So he did that, and now the first satellite was launched in October 4th, 1957. The first man-made satellite was launched was going around the Earth, called Sputnik. This rocket was developed by Sergei Korolev. He made a very big intercontinental ballistic missile. We are trying to do big ICBM now, but he made it in those days, 57. He made a very big rocket, intercontinental ballistic missile. The same missile was used to put the satellite also in the orbit. So after the World War, a race began between the world's two superpowers, Soviet Union and the United States of America, to see who would be the first to space. So the Soviet Union proved they are the leaders in the space program. And not only that, then immediately in 57 itself, they put a dog into the orbit. Then in 59, they put the first satellite to the moon. This is a lunar mission. In 1959, they made the lunar mission. And then they made in 1961, Yuri Gagarin went around the Earth. He's the first human to travel into space. Then a lady also went. That is 63 she went, Valentina. Then you have got another man, Alexei, he walked in space. So this is the all first to be told. Then the Americans got wild, so they wanted to do something. So they depended on von Braun. Then von Braun made this is a von Braun's satellite. So different type of satellite, you can see that. And that was put on a rocket, which they developed Redstone. And they put this up, and that has worked well. So, but very short time. So the three men responsible for the success of Explorer, this is called Explorer, that's a satellite name. First satellite, which was launched in 1958. So these are the people, and they built it, and von Braun was responsible for it, to develop the Redstone, which put the satellite in the orbit. So this America entered into space in 1958, 1 year later, or a few months later after the Soviet Union. So if you see the countries capable of launching space rockets, first, when did they do the first time? You see Soviet Union 57, 58, so United States. Then it says 65, France, 70, Japan and China. Both the people launched in 1970 their satellite. 71 is the UK. And then 79 is ESA. In 1980 is India. First, our SLV-3 launch successfully launched a Rohini satellite into orbit in 1980, July 18th. 88 is Israel. Then 91 is, these are Ukraine, Russia and all part of the Soviet Union, but split. No, the Soviet Union disintegrated, and then individually they started putting their satellite. But we don't count that. Now we talk about Iran 2009, North Korea 2012, South Korea 2022, Israel 88. So you see, Soviet one side, America one side, Europe one side, the USA and all those things one side, India another side, and Israel, North Korea, South Korea, and Iran. These are the other countries who have made it. So today, these are the countries who have got the capability to put satellite in the orbit. They proved that their own launch vehicle, using their own launch vehicle. Then they thought that they should take a lead over the Soviet Union, the Russians. So that von Braun thought that he should make a very big rocket, that is Apollo. The decision given by John F. Kennedy that the America will put their men on the moon and safely return. They will return. So this is the one which challenged the Soviet Union, but Soviet Union did not do. The Americans proved that they could go to the moon, land on the moon. And there are a number of questions whether they say, is it true that they have really gone? I'm telling you, all are true. They have gone. The 12 Americans have landed on the moon. Apollo 11, 12, 14, 15, 16, and 17. Six into 2. 12 Americans have walked on the moon. This flag, whether is it, some people say, well, how can it fly? It's not flying. There's a rod there. It is fixed in the rod. There's no flight or anything. There's no air there. Okay, so this is the one which made the Americans to take a lead in the space program over the Soviet Union. Now, if you see the America, they have got, after the Saturn V, which is a huge one, they have now recently made another rocket called SLS, Space Launch System, which is also equal to that, and it's very capable. You can put a human being on the moon in 4 days' time. So these are the other bigger systems which they have developed. Main thing is the space shuttle. But now they stopped the space shuttle, which why they stopped and all, we will be understanding that at a later date. So this is a comparison between the Saturn and the SLS. So the interesting thing is the price. You see that it is a 1.49 billion each flight, $1 billion. Now this is $4.1 billion, so huge. So its cost is very huge. They can afford to do that big thing. But this budget is getting cut by Trump now. So the space program in America is getting into certain problems in the recent times. So others also started. This is a very big other launch vehicle called Ariane. This is a European space agency they have developed. This is also a very huge rocket. It can put about 6 to 7 tons of satellite into the orbit. All our bigger satellites, INSAT satellites, GSAT 11, all these big satellites which we cannot put, we go to the Ariane to do the launch. And these Chinese, they have got a very series of rockets they have got. They are also, one of the leaders today. They have overtaken the Europeans. They are very, very close to the Americans now. And Japan, they have developed a very big rockets called H2. And this H2 rocket is also very big. And they are all using the, cryogenic. See, if you see this big solid booster and cryogenic core vehicle. This also like that, cryogenic core vehicle with solid rockets to give the initial boost. And these are the Russians. They have got the Proton and different types they have got. All big rockets they have got. And SpaceX has come in a big way now. So these are the dominant rockets which have come. So if you see the SpaceX is very interesting. They have got different types of Falcon rockets, and then the huge rockets also they have made. And 26 tons to GTO is a very big thing. And 16.8 tons they can send to Mars. So these are heavy rockets which they have developed. So worldwide, you see that there are so many rockets in many countries, and these are the bigger rockets, Saturn. These are to the Russians, which they dropped that, and now the Falcon, the Elon Musk rockets are taking a big shape. Space shuttle, as well as the Buran from Russia. Buran was used only once; they stopped that program. So this continuously went on. Space shuttle. So you can see all the rockets. Our rockets are also. So now the interesting part is that we have got an orbiting station called International Space Station, and this station was controlled by two ground stations. One in Moscow, this is the Moscow station, mission control, and there's another one in my USA, in with them. So these are the two stations, but there are a lot of these a joint program. So many astronauts have gone to the space station to do zero-G experiment. Gravity is zero. So our man has gone recently, Supla has gone. So this is a very important study which they have made, and from 2000 to 2025, that is 25 years, this is orbiting. Very, very important station. For 420 kilometer it orbits, and it weighs around 420 tons. Length is 73 meters, and the width is 109. This is a width and this is a length, 109 meters. So it's a big one which is orbiting. So we have reached that stage. Now all these things, when you talk about the rocketry, so there is some basic principles are involved. So the Newton's laws of motion is a very important thing to understand. The first law, that objects at rest remain at rest, and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. This is the first law. Second law is force equal to the mass time acceleration. F is equal to ma. Third law is for every action there is equal and opposite reaction. This you have studied in the school. So I am just telling you, let us understand what it is. So this is the first law. You hold a thick steel ball. You hold it. When you're holding, the thick ball is giving a weight on your palm, and you are giving a balancing force called lift. So this is called gravity. The ball is giving a gravitational force, which is weight down, but you give up a force that's called lift. So this you should remember this when I am talking about the rocket. You should remember this. Now, so if you leave your hand, that will fall. So that is, as long as you keep it in rest, it will also be, ball will be in rest. If you remove your hand, the ball will not be in rest. So here what we are understanding is the force of gravity is trying to pull the ball downward. But what you are while at the same time, your hand is pushing against the ball to hold it. Okay. Right? So this is you are trying to balance it. But if you change the force, then things will be different. For example, when a ball is at rest, it's at rest. But if you give a kick, it moves. That's the first law. Or if it is in motion, you put a brake, the goal post, if it's a brake, then it stops. This is again the same effect. That is, you are trying to change the motion by putting an unbalanced force. This you see cycling. There's a stone or something, thick stone. He has gone, he is falling. This also, you see, if he is going continuously, he will be continuous in motion. But his motion is stopped by another force. So this is the principle of the law of motion, that whenever there is any unbalanced force is acting, the rest or motion will change. Second one is that you see there's a cannon. There's a cannon. You fill with the stuff inside and put a ball here. So if you put a fire, the fire creates a force, and because of the force, this ball moves here. But when the ball moves there, there's a backward push by the cannon. So the cannon, when it is moving backward, that force, see that force is equal to m ball into a, its acceleration. Similarly, when this is moving, the m of the cannon into a of the cannon, which is pushed other side. Both are equal. Okay. This is the principle of the second law. So here also you see action, reaction, you see same thing. So let us see the action, reaction. This I have told you earlier, when the fuel burns and the rocket is vertical, when it burns, the rocket goes up. Let me see how it goes up. You see that? So that is the same principle which I explained last time also, the action, reaction. Now, another thing which we should understand in a rocketry is lift, drag, weight, and thrust. There are 4 forces. The rocket has got a weight. That weight will act on the CG. And the CG, at the CG, the weight will be attracted. That's a due to gravity, the weight will come down. That is the mg. M is the mass into G is the gravity, that's the weight. So it pushes, it pulls it down. But then you are giving a thrust, you are giving. Then because of the burning, and then you are giving a thrust. The thrust should overtake the pulling down, it overtakes and pushing the rocket to the direction. Same time, there are 2 other forces acting. One is called lift. This is trying to pull it up, whereas there's another one called drag. This lift and drag comes because of the configuration. You know, when I showed you the last time, the Wright brothers, I talked to you about lift and drag. So they explained nicely. So these are the very important forces in the design. This particular thing depends on the design of the rocket. This we will be seeing it later. I will explain to you in detail. So this is acting, lift and drag is acting under the center of pressure. So there are 2 things which we should know. There's a center of gravity and center of pressure. Center of gravity should be always in the forward, and the center of pressure should be at the backward. Then only the rocket will be stable. This you keep remember, then we will explain it later. This I will explain to you more by an experiment done by.
And open at this end, this is called the muzzle, and there's a small hole called the touch hole that we use to transmit fire to the main charge. So we're going to begin by taking a piece of slow burning fuse and placing that in the touch hole. And then we're going to charge this with gunpowder. So
that's a fuse. What he's saying that is to be fired, but he is giving the charge now.
I put my finger over the brass nozzle. I press the valve and tip it upside down, and powder trickles into that brass spout. So we're measuring a precise quantity of gunpowder. And I release the valve and turn it right way up again. And we have a measured quantity of gunpowder in the spout. So I'll place that into the barrel of the cannon.
The gunpowder is filling with the gunpowder.
It's a double dose. Here's a double dose of gunpowder going into the cannon. So that's the gunpowder in the barrel. I'll put this safely out of the way. Now, to keep the gunpowder in the barrel and keep it up against the fuse, we're going to use a little bit of wadding. So this is sort of fireproof wadding, which I'm going to put into the muzzle of the cannon, and then use this round rod to pack the wadding and the gunpowder tight up against the fuse. Now, at this point, we'd put our cannonball in. We're not going to do that today. So instead, we'll simulate that by using a bit more wadding. I'm going to put some more wadding into the barrel. And again, just pack that down. And then finally, to stop the ball rolling out, as it were, we'd use a bit more wadding. So why not? Let's do a bit more wadding. It is the science festival after all. Okay, so we've got this wadding nicely packed down. Our cannon will be loaded and it's now ready to fire. So I'm going to light the fuse From where I'm standing, it's quite noisy, so I'm going to be covering my ears. If you're near the front, you may wish to do the same. When the fuse burns down and the cannon fires, I want you to look carefully what happens to the cannon. So here we go. Okay, so as you saw, the cannon shot backwards. We call that recoil. And this is a very basic principle of physics. It's the idea of conservation of momentum. So when the cannon fired, hot gases and pieces of wadding were shot out of the barrel at great speed in this direction. So those pieces of material had a lot of momentum in this direction, but the total amount of momentum in the world can't change. And so the cannon acquired some momentum in the opposite direction. So this is the basic principle of the rocket. By firing gases very fast in one direction, we create a force in the opposite direction. Now, this cannon is very nice, but of course the force was created sort of all at once. We just had an explosion. If we want to build a rocket, what we need is a nice steady push that goes on for a long time. And to see how we can do that, Chris in the department here has been building this lovely demonstration. And as you can see, this is a go-kart, but it's a rather unusual go-kart because this is powered by a carbon dioxide fire extinguisher. So the fire extinguisher is at the back, and inside the fire extinguisher is carbon dioxide that's been compressed so much that it's turned into a liquid. So there's a lot of carbon dioxide in the fire extinguisher. When I press on the pedal, it will open the valve and the carbon dioxide will escape with great speed in that direction. And so it should create a force in this direction. So what I'm hoping is that it will push the go-kart forward. So should we give this a try? Are you ready, Chris? Okay, all set? Okay, here we go. Okay, so that's the principle of the rocket. On the go-kart, we had gases escaping very fast in one direction, providing a force in the opposite direction. But we used a whole cylinder of carbon dioxide just to get a few meters. It wasn't very effective. And the reason is that compressed gas doesn't really contain enough energy. We need some way of getting a lot more energy out of every kilogram of propellant. And to do that, we're going to turn to chemistry. Now, you're all familiar with the motor car, and in the motor car, we take a chemical, a fuel, either petrol or diesel, and we react it chemically with the oxygen of the air. We call that combustion. That produces energy, which drives pistons, which turns the wheels on the car and drives the car forward. Could we use that same principle of combustion to produce not a turning of wheels, but rather a rocket-like force? Well, we can, and the next demonstration, if we could bring this on, please, shows exactly that principle. And again, it's one that's very familiar. It's called the jet engine. So in a jet engine, we burn fuel. In this case, it's a fuel called Jet A1. It's a bit like kerosene. I have some of the fuel in this bottle. It's reacted chemically with the oxygen of the air to produce an escaping jet of gas traveling very fast, and that produces a force in the opposite direction. So we'll just set this up. And when this is running, it will be quite noisy. So I'm going to wear a pair of ear defenders for this. So this is controlled by a little computer. So I'm just going to switch on the computer. And now we're starting the engine. This will take about 20 seconds or so to start. And it'll run up, first of all, to idle power, which is about 40,000 RPM. And then when it's at idle power, I'm going to ramp it up to full power for just 2 seconds and then switch it off. Why 2 seconds? Well, at full power, it'll be doing 150,000 RPM. It'll generate 100 newtons of thrust. That's 10 kilograms of thrust. The exhaust gas temperature is 700 degrees, traveling at 1,500 kilometers per hour, consuming 1/3 of a litre per minute of fuel and producing 20 kilowatts of power. So here it is ramping up. It's at 18,000 RPM. 25,000 RPM. 35,000 RPM. And it's now at idle power, just over 40,000 RPM. And I'm now going to take it up to full power for 2 seconds, and then I'll shut it down. You ready? Here we go. (1,500 feet). So it does this by producing lots of gas. Well, we've got an experiment over here to find out how much gas is produced by a rocket motor. So I have a slightly larger motor. What we're going to do with this motor is to burn it underwater and collect the gas so we can see how much gas is produced. So in this apparatus, we have a tube full of water. We have another one of these motors. It's in a plastic bag so it doesn't get wet, and it's underwater. And when the motor burns, it will produce gas, and the gas will displace the water in this tube, and we'll see just how much gas is produced. Now, to set off this motor, we have an electrical match inside the motor, and it's connected by these wires to the thing which is really my favorite way of setting off explosives, which is this. So this is actually a genuine, very slowly it burns. So you see it's burning slowly along the track. It's taking several seconds to get from one end to the other. That's burning just in the open air. But in a rocket, we take our fuel, our propellant, and we confine it in a rocket chamber and allow it to build up pressure. And that build-up of pressure does two things. It increases the rate of combustion, and also the high pressure means the gases come out of the end at high speed, and that gives us extra thrust to our rocket. But we have a problem. If we confine that pressure too much, things can go wrong. And I want to illustrate what can go wrong with the help of another volunteer. Should we have a volunteer from this side? Who wants to come on down? Would you like to come down second row back? Yes, let's have a big hand for our volunteer. And face the audience, what's your name?
Jack.
Jack. All right, Jack. Well, just behind you here in this safety hood, we have another 2 grams of that smokeless powder, but this time it's inside a cardboard tube, and the cardboard tube is bound up with lots of tape, so it's very tightly confined. And again, we have an electrical batch inside the tube, so we're going to set off the powder. This time it's very tightly confined. We'll find out what would happen to our rocket if we don't get the design quite right. So if you'd like to come over here. So again, we've connected it up to this exploder. So don't operate that just yet. My prediction is that the rate of burning of that powder will be increased so much that we're going to need ear defenders. So I'm going to give you ear defenders. I'm going to wear ear defenders, and you may wish to cover your ears for this. So this is 2 grams of that smokeless powder, just like we saw in the track, but this time very tightly confined. Okay, off we go. Well done. Good point. To turn and look at the physics of rocketry. And the physics of rocketry also presents us with some very interesting challenges. And to illustrate this, I'm going to need 2 more volunteers, please. I think in the stripy shirt, you were very quick. Yes, on the end, you'd come down. Somebody from over here, you're very keen, so why don't you come on down? And a big hand for our 2 volunteers, please. Right, if you'd like to stand face the front, what's your name? Louis. And face the front, stand there, face the front. What's your name?
Albert.
Albert. Right, I've got 2 poles, and they're identical. They have little pegs on the end. And what I want you to do is to balance these. So if you hold out a finger like that, what I want you to do is to balance that on your finger and keep it vertical. Okay, manage that. I want you to do the same thing. That's it. turn your finger the other way up, be easier. I'm going to make it a little bit harder for you, so I'm going to turn it up this way, all right? All right, now concentrate really hard and see if you can keep it up, right, okay? Oh, well done. Okay, have another go. Have another go. Try really hard, okay? Got it? Oh, excellent. Fantastic. Thank you both very much. Thank you. So what you saw there was that when we try to balance the stick this way, it's very, very easy. We call this stable. We say this stick is stable. What that means is that if I nudge the stick a little bit, if there's any sort of disturbance, and I nudge the stick, it comes back to where it was. If the stick is displaced, it moves back to where it was before. That's called stable. That's very easy. When the stick is this way up, however, we call this unstable. Even if I manage to balance this and get it exactly vertical, the tiniest disturbance, as it starts to move, it keeps moving in the same direction. It moves away from where it started. We call that unstable. And the problem we face in rocketry is that all rockets are unstable. If we think about a rocket, imagine this rocket is taking off, it's going up vertically, but there'll be some little imperfection in the rocket, something that isn't quite symmetrical, or a little gust of wind, or something that will nudge the rocket and point it in a different direction. The problem now is that the thrust, the force, is now also pointed in a different direction. So if it starts to deviate, if it starts to change course, the thrust will propel it in the new direction and it will keep on turning. So if we just fire the rocket, it won't go in a straight line, it'll fly very erratically. And we have to solve that. And we've seen from our volunteer how to solve that. When he was balancing the stick, what he had to do was to keep moving his finger around. Okay, we call that active stabilization. And that's how big rockets were. I think one of the most impressive pieces of engineering of all time is also the largest rocket ever built that's flown successfully. It's the Saturn V. And it took astronauts to the moon in the 1960s. And the Saturn V was an extraordinary piece of engineering. It was the height of a 36-story building. It weighed 3,000 tons. And the first stage burned fuel at the rate of 15 tons a second. So imagine this 36-story building lifting off the ground on 5 columns of flame produced by burning fuel at 15 tons a second. And the whole thing is unstable. So to stabilize it, what they had to do was have these engines, and each engine is the size of a small house, to have these engines swing backwards and forwards and be moved by gigantic hydraulic rams. So as the rocket takes off, as it starts to tilt one way, the engines are pivoted while they're burning 15 tons of fuel a second to correct the trajectory of the rocket. It's an extraordinary piece of engineering. Unfortunately, if we want to fly rockets in the Earth's atmosphere, we can do something that's a lot simpler. We can actually make use of the air to provide stability. And I'm going to try to demonstrate this using an experiment which will involve everybody in the lecture theatre. So hopefully just before the start of the lecture, you constructed these paper aeroplanes. Now, the aeroplanes are identical except for the location of the paperclip. On the red aeroplane, the paperclip is at the back, whereas on the green aeroplane, the paperclip is in the middle. So if you could all check that whichever color you have, you've positioned the paperclip in the correct place. Okay, what we're going to do now is the thing that you've always wanted to do, which is to throw paper aeroplanes at the lecturer. So I'm going to be the target. Your job is to hit me. Now, I'm going to give you a piece of advice that might make it a bit easier. When you throw a paper aeroplane, it doesn't fly horizontally, of course, it descends under gravity. So it's no good throwing them directly at me. What you need to do is to aim above my head. And I suggest you aim for the top of the white screen. And then the aeroplane should descend and reach me. What we're going to do is, first of all, just throw the red darts. So just all the green darts stand down. I'm going to give you a countdown. 3, 2, 1, go. When I say, I want everybody with a red dart to try to hit me. Okay, are you ready? Red darts. Okay, 3, 2, 1, go. Okay, oh. That's cheating. Okay, let's see what happens now if we throw the green dart. So everybody, the green dart, get ready. Okay. 3, 2, 1, go. Okay. Okay, well, as you can see, the darts at the front are all green. For some reason, those green darts flew a lot better than the red darts. The reason is that the green darts are stable, whereas the red darts are unstable. And I can explain why the difference occurs using a little model. So in fact, rather than using a model of an aeroplane, I'll use a model of a rocket. So this is our rocket model. And the first thing we need to understand is a concept called the center of mass. So if I take my rocket and I balance it on my finger, somewhere about there, I think. So the point where it balances is called the center of mass. And we can think of all of the mass of the rocket as acting at that point. And that point acts like a sort of pivot point. When the rocket is in flight, if there's some disturbance that nudges it off course, it tends to pivot around the center of mass. And so I've marked the center of mass on this rocket with this symbol. And so this is the point about which the rocket can pivot. The other idea we need is called the center of pressure. So let's imagine a rocket in flight. We think of the rocket as traveling very fast and the air through which it's flying as being stationary. But imagine you were flying on the rocket. You would think the rocket was stationary and you think the air was coming towards you. We call that the relative wind. So if you're on this rocket, the air is moving towards you. And so there's this wind blowing on the nose of the rocket. Now imagine the rocket is nudged slightly to one side. The wind will act on all parts of the rocket's area, but the overall effect of that is as if the wind was acting in one place. We call that the center of pressure. So roughly speaking, the center of pressure is the place where the area in front is the same as the area behind. So this particular rocket has the center of mass behind the center of pressure. That's a bit like your red rockets, your red aeroplanes. On your red aeroplanes, you had a paper clip at the back, and that moved the center of mass behind the center of pressure. So let's see what happens to an aeroplane or a rocket which has its center of mass too far to the back. So here's our rocket in flight. This is the relative wind as the rocket flies through the air. But if it suffers a small disturbance, it points off in some other direction. Okay? This is unstable. As soon as it starts to change course, it's pointing all over the place. So it's flying very erratically. That's an unstable rocket or an unstable aeroplane. So what we need to do is to change things around a bit so that the center of mass is in front of the center of pressure. And on the paper aeroplanes, we did this by moving the paper clip from the back to the middle. So here's the center of mass, that's the pivot point. The center of pressure is the same because these shapes are the same. So let's see what happens with this rocket. It's flying in this direction. And it's quite happy. If there's a disturbance, it points back towards the direction it was going. So that's why this is stable. Now, we could make our rocket stable by fitting giant paper clips on the front of them. That would not be a very good idea. We could add lots of lead weight to the nose cone, but that would be very wasteful because in rockets, it's very expensive to take mass up into the sky or into space. And that mass is very precious. And we don't want to be carrying empty weight, as it were. So I'm going to launch my fireworks from this spot. It is happy. What would happen, however, if we included a few rockets in our display? Well, let's think about this. We launch this rocket vertically, but the wind is coming from this side. So it acts on the center of pressure and it tips the rocket in the direction of the wind. But the rocket's still burning. So it's now going in this direction and it's turning the whole time into wind. So rockets are very strange things. When you launch them, they fly into the wind. So the empty rockets are all going to land here and are already blown downwind into our fallout zone. Here are for a 6-inch diameter rocket. So these will be assembled into a large, much bigger rocket even than this, as an moving down and slowing down as it climbs against gravity. And eventually it reaches the highest point, we call that the apogee. And after that, it starts to descend under gravity. Now, the apogee is the point at which it has the slowest speed. So that's the point where we want to open the parachute, because if we open the parachute when the rocket's traveling fast, the parachute will just be destroyed. So we want a way of opening the parachute at the highest point. There's one way to do that, detecting the point at which. So, all right, well, if we'd like to, in order to achieve a nice soft landing, if we cool it down enough to around minus 183 degrees centigrade, it will turn into a liquid. And we can achieve that by using another very cold liquid called liquid nitrogen, which has an E. And I'm pouring liquid oxygen onto the toast. I guess in the spirit of the science festival, I'm going to be quite generous with this. So there's our toast, soaked with liquid oxygen. And now we'll set fire to it and see how well it burns in this very concentrated form of oxygen. And it's worth remembering, every time you eat a piece of toast, it's quite an unpleasant material, but we've got a small quantity in the test tube, rocket engine, which is somehow powered by oxygen. That colorless liquid is called carbon disulfide direction. This motor. So this is our rocket, Albert. Right, I've got two disappeared. Matter can't just disappear like that. What's actually happened is burned very efficiently. What we have there is a mixture then of the fuel, methane, and the oxygen, 2 atoms of oxygen. So for the carbon.
So this is available in the YouTube. This what I have shown you. You can go through that in detail because this explains fully the principle of the rocket. So in India, we started the rocket development by Dr. Sarabhai, and he has started the whole thing in a fishing village called Tumba near Trivandrum. Why he started in this village? This is the village, the only place where the magnetic equator of the earth is passing through. When the magnetic equator is there, you get the equilibrium, and that electrojet will be able to give accurate data of the atmosphere. That is why he started that program, that place, and dedicated that place to the whole world. So all the people started coming in. So this is the first rocket launch in November 1963. This is a Nike Apache rocket of the America. The NASA has come and launched. Like this, 60,000 rockets have been launched from this place to study the upper atmosphere. All the world people use this station. This station is called Tumba Equatorial Rocket Launching Station, called TERS. And in this, there is a church here. That is the place where the design of the rockets were made. And Dr. Abdul Kalam worked in this church. And this church is the place where, today we have a very good museum. If suppose some of you wants to go to Trivandrum, please go to this museum. This is a very space museum, very good museum to explain how the space development happened in the world, in India, and what are the developments we have done. All these things are explained in this museum. Now, after doing the sounding rockets, Sarabhai thought that we should communicate to the people. So he 2,400 villages, he communicated using a satellite called ATS. This is an American satellite. He borrowed the satellite for our program. And where there's no electricity to these villages, but he brought electricity through the mobile vans. and put the TV, black and white TV at the time. All he showed to the people, and that is called SITE program, Satellite Instructional Television Experiment. So that was a big hit in India when there was no TV. Now he also did another program, communication satellites he got from Europe, and he communicated the people. This is a STEP program which he launched on the communication. Then he thought that we should have our own satellite and launch vehicle. So he started designing with the help of our people, the first satellite launch vehicle and also the communication satellites. So his theme was very clear. He gave a 10-year profile to launch the communication satellite. And he was very much convinced that India will be second to none in using advanced technologies for solving problems of common man using space technology. So this is Sarabhai, you can see Sarabhai, and the next man is Satish Dhawan. So these two people made India a space leader. And the initial starting was on these sounding rockets. Sounding rockets are the one which go up and then try to study the upper atmosphere. So there are different types of sounding rockets. These are RH2 Rohini 200. 200 means 200 millimeter diameter, 300 millimeter, 560 millimeter diameter, and it can take a payload up to 100 kg to 470 kilometer. So straight up it go the 470 kilometer, and different payloads are used to study the atmosphere. You can see Abdul Kalam here and his friend Aramdan, who became later the director for the satellite, all satellites building, and they are making the payload required for the RH200 at that time. So these are the different sounding rockets which were developed by ISRO, which can go up to 470 kilometers. Up it can go. From sounding rocket, we thought that we should graduate to the launch vehicle. Sounding rocket will study the different atmosphere. You know, if you see the atmosphere, we got troposphere, stratosphere, mesosphere, the thermosphere, exosphere. These are the very different spheres we have, and also the ozone somewhere here. So these are the things which we need to study. So this study has been done. So about the ozone, everything they studied. So these are the rockets developed. First, this was the SLV-3 satellite launch vehicle, which can put a 40 kilogram satellite. Then the ASLV, augmented satellite launch vehicle, with the two big strap-ons like this first stage. Two other first stages become strap-ons. So this gives a 150 kilogram. Then we designed the PSLV, which can put nearly 1,000 kilogram into the low Earth orbit, and about 500 kilogram in the in the polar orbit. Different polar orbits are there. So it's a 475 kilometer is about 1,860 kg it can put. So if GSLV, that is a geosynchronous launch vehicle, and then GSLV, this is the bigger launch vehicle which we are having. We will see that. So the first launch of the SLV-3, and you can see Dr. Abdul Kalam operating the whole thing. He was the mission director, and we were all his team mates. These are the core team members, including me. So we were working with him to develop this launch vehicle. This is the launch vehicle. You can see this launch vehicle SLV-3. It has got 4 stages, and this is a heat shield protecting the satellite. This is a satellite called Rohini satellite, and launched successfully, and India became a member of the Space Club. So initially we tried with the low Earth orbit for any scientific experiments. Even now we use low Earth orbit, as well as the GPS is also in low Earth orbit. And the other thing is called polar orbit. Pole to pole, the satellite is put to this orbit. And because it is in the polar orbit, about 500 kilometer altitude, and Earth is moving west to east, we will be able to photograph any part of the Earth. So we'd say all places on the Earth comes under the visibility of the satellite. There is a polar satellite launch vehicle. This is the polar satellite launch vehicle. to put the satellite in. So then we have got the geostationary launch vehicle. This is a GSLV.
Vehicle lifts off. He's solid in the
So this puts the satellite in the geostationary orbit. This orbit is 36,000 kilometers away from the Earth, away from the equator. It is over the equator. It is moving, this is the orbit, and the satellite is put in a speed synchronized to the Earth. That means higher speed, which is synchronized to the Earth. So always the satellite will be beaming to only a particular place of the Earth. All our satellites, because of the communication satellites, are looking at only India. So we have 24 hours, our mobile phone communication, all these things are happening because of this satellite in this orbit. So these are the three orbits which you should know. We will explain that in the later classes. We will understand more about the satellites and how they work in different orbits. Now you just see how you launch a GSLV. This is a GSLV launch. You can just see the GSLV launch.
All stations stand by for the time mark. Mark minus 1 minute and counting.
Minus 1 minute.
Minus 55 seconds.
All flaps are out.
Minus 50 seconds.
Sequences are out.
Minus 45 seconds. Minus 40 seconds.
Minus 20 seconds.
Minus 35 seconds. Minus 30 seconds.
Real-time programs activated.
Minus 20 seconds.
Okay. Minus 25 seconds.
Alert and VSPP open.
Minus 20 seconds.
Minus 20.
15 seconds.
Fire out.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, plus 2,
200 ignited.
plus 3,
Vehicle lift off.
plus 4, plus 5, plus 6, plus 7, plus lift off normal, plus 9, plus 10
Just
seconds.
heard the announcement. Lift off normal.
Plus 15 seconds.
15 seconds into the flight.
Plus 20 seconds.
Escort.
First stage performance normal.
Indicated as
Plus 35 seconds.
These are the boosters, two
20
big
seconds.
boosters they are burning, giving a very large thrust to push it up.
Plus 35 seconds.
And after this burning about 100 seconds, this will be jettisoned and the core will start. The core is a liquid core.
Plus 45 seconds.
6, 7 kilometers.
Plus 50 seconds.
50 seconds.
First stage performance normal.
So about 100 seconds will go.
75 seconds. Vehicle at 18 stage, which again is a very important activity. If you look at the plots of the time versus altitude and velocity, we see a very close match with the pre-flight and the flight predictions.
L110 ignited.
Yes,
The
L110
second stage, that is core
booster has
stage
been
ignited.
ignited at exactly 114.9 seconds. The vehicle is at an altitude around 51.5 kilometers.
Normal.
And L40 ignition and performance has been indicated normal. हम इस वक्त रॉकेट के पहले चरण के फेज से we heard the announcement S200 solid stopper has been successfully separated at 141.2 seconds and vehicle has entered the closed loop guidance in the second phase of flight. और अभी हमने range operation that traveled 200 kilometers from the launch base. It's an altitude around 117 kilometers.
Altitude and the
And
range.
heat shield has been successfully separated at 225.7 seconds.
See, this is the velocity buildup and the altitude.
As far as the velocity is
and also the
concerned, we
range.
have
they are
almost a
showing.
2.5 kilometer velocity has been imparted to the vehicle.
The 250
The
range.
final,
is the range.
Injection velocity is order of 9.8 kilometer per second. The next important event will be the
L
separation of
what's normal?
so L100. So 320
So you
seconds.
can
We
say
should
it
get
has
the
gone
announcement
to
of separation of the
166
110.
kilometer height.
Indicated as absolutely. And just now we
Altitude
heard the
200
announcement.
kilometers altitude.
Normal. So we'll have a burn time of almost 600 plus seconds into this flight. Flight is at 90 into a GQ orbit will be imparted by this very important cryogenic stage. This is it, a very close match with the.
You can see that the red is the
screen
prediction and
altitude.
this is the actual thing going.
The red one is the pre-flight prediction, and the one, the dotted one is the one where the vehicle is presently flying. So all time versus altitude, time versus velocity, a very close match. 4.6 kilometer per second. The view of the
we have to
launch
achieve
control center.
nearly 9 kilometers per second velocity we should achieve.
Meters, and it has reached an altitude around 233 kilometers.
10, it has come to 10.
Maybe another 30 seconds to go. 9:44 seconds.
So we are now 172.
Engine shut off.
So see 25 engine shut off.
See that velocity has been achieved here.
The vehicle is at an altitude of almost apogee of 30 kilometers.
So you can see that velocity has been achieved here, the height. So then the propulsion is cut
Maybe
off.
another 30 seconds to go. 9:44 seconds.
Engine shut off.
So see 25 engine shut off command has been issued. So this side 19 satellite is successfully separated. At
satellite is getting separated. This is a camera view of the separation of the satellite.
So GSLV Mark 3 rocket ने अपनी पहली successfully separated. और मिशन कंट्रोल सेंटर में इधर
So this is a
सभी वैज्ञानिकों की
geosynchronous.
जो आपके स्क्रीन पर देख रहे हैं.
Before going to the geosynchronous, they put it in a highly elliptical orbit. Then later they correct it. So this is how the rocket launching takes place. If you want to go to Sriharikota to see the launch, they will not allow you inside. They will have to see from outside the whole thing going up. It will be interesting sight to see the takeoff. But if you go in the normal time, you will be able to see this control center and other details. We will take you some time to Sriharikota. Now this after the Sarabhai's vision and Satish Dhawan's structured programs, we have seen today number of satellites have been launched. So number of the communication satellites, remote sensing satellites in the polar orbit, then IRNSS, that is our GPS, Indian GPS system, then docking of satellites in the orbit, planetary missions going to the moon and going to Mars, then Aditya program to study the sun. All these things are happening and we are very strong force today in the space technology. We are self-reliant in space technology. We are very competitive power, space power, along with 3 other people. One is the America, number 2 is Russia, third is China, and fourth is India. That is a rank we are having now. And we are going to, but there are certain things we are first. For example, reaching the South Pole, we are first. Putting 104 satellites in one PSLV, we are the first. And Mars mission, the first attempt itself, we were successful. So that way, we have also taken some lead over others in certain programs. So now whole our attempt is on the space program to put the man in space. So this is you will see the astronauts, Indian astronauts. They are trained by Russia. This is a place called Gagarin, the cosmonauts training center near Moscow, where our earlier people know we have 50 students whom we have taken there. They have seen this facility and they have met 26 astronauts getting trained there. So it's a very interesting place to see in lifetime how the astronauts are getting trained. So this 1 year training was there for these 4 people. Out of that, Shukla was chosen to put in the, the International Space Station. He has gone. So these people will be going to space and later they will be walking in space and they will be landing on the moon. and establish a factory also on the moon. This will happen in the future. So the sequence is very interesting. So ISRO has made a plot of the sequence. This is the Chandrayaan program, Chandrayaan 3. Now there's very soon you will hear about Chandrayaan 4, where we will be taking the sample and coming back. The samples will be brought back to us, and then there will be orbit refueling will also be attempted later. Then is a long mission. A number of the orbiting around the moon will be more, and also going there and taking off. All those things will be tried out before we send the human. Human will be sent to the moon in 2040, and before that we'll be having an orbiting platform. We'll make so this and spacewalk. All these things will happen. So this humanoid in the moon, we are going to put a humanoid first. We are going to launch to the moon. So many new things are going to happen, and new launch vehicles are coming to go faster, because whatever we have, this LVM-3 has a limited capability. We need 40 days to reach the moon. So we want to reach the moon in 4 days. So that type of system will be made. China has got, Russia has got, Americans have got, they are all having system to go in 4 days. Elon Musk has got. So we should also have a better launch vehicle which will be capable of making movements in 4 days time to the moon. So that is the thing. And then finally lunar base. 2047, India, when it is becoming 100th year, we will be having our complex, that is the factory on the moon. So that's what I will tell now for this class. So we will now get into question mode. So you have seen now that just to summarize to you how the whole thought about rocket came, explosive, then explosive utilization in a rocket form, and then the people came, the theory came from Konstantin Tucholsky. He talked about this rocket, and he gave the equation. Rocket equation was given by him. Then the rocket was proved by Goddard, and bigger rockets were developed by the Germans. And then we thought we should go to space, so orbit the satellites. And many countries came forward to do that. And today there are so many rockets in the world. And then we thought that we should know about the principle of that. All the rocket principle is around the laws of motion by this one. So we have studied the Newton's laws of motion, 3 laws, which are the basic principle of the rocket principle. And how it works we have seen. And then we have seen the Indian side, how it has all become, and we have rockets, and then we have achieved bigger rockets. We have launched many of them. Today we have become a space power, and we are going for ahead with the missions to the space, Gaganyaan, people to space, Indians to space. Okay. Shall we go for questions?
Yes, sir.
So I have taken out my slides. Now we'll let us discuss the questions.
Yes, sir. Yes, sir. Yes, sir. Thank you so much, sir, for the session too.
So you joined. Okay, Google. Google, what is
Yes, sir.
tomorrow? What is the program? 27th, you know?
Yes, sir. Yes, sir. Tomorrow many online programs are going on, sir. And okay, maybe in our foundation also at the House of Kalam, they are doing some STEM projects, sir. So that they are planning up. I heard some our ISRO chairman is also planning to visit like that, sir.
Like
since today he is in NIT Trichy, sir, for convocation.
Okay. So he is going to this Dr. Kalam's place, huh?
Yes, sir. Yes, sir.
Okay.
I have seen the poster in the Facebook, sir.
Okay. Thanks.
Yes, sir. Maybe we will plan up some event, sir. Maybe tomorrow with online also. I'll call you, sir.
Okay.
So yes, sir. Thank you so much, sir, for the second session of our rocket science. So maybe
So
now it is open.
tomorrow we are having the third session.
Yes, sir. We are having the third session.
Okay.
So since for Abdul Kalam's anniversary 10th year, sir, so we can have that celebration also with all our children also.
Yes.
So maybe question answer sessions can be started. So students can raise your hand, and accordingly we can put you into the presenter mode.
Prasanna Venkatesh. Salem.
Sir.
Salem. No. You are from which place? Sairam.
Sir. Yes, sir. Sairam Metric High Secondary School, 33 sir. I am studying 11th standard.
Okay.
Sir, my question is, are used in rockets to control its position and speed?
Repeat your question, sir. It's getting cut.
Sir, my question is to control rockets are used. Which sensors in rockets used to control its position and speed?
So you are talking about the controlling the rocket, you know. There is a separate chapter we are
Yes,
going
sir.
to deal with on control system. There's
Yes, sir.
prescriptions are there, different types of control systems, how the rocket is maintained in their trajectory. These are all going to be there. That time I will explain.
Okay, sir. Okay.
Next is Savita. Savita, unmute. See, they have raised their hand, but we should unmute, then only they will be able to. Savita.
Sir?
Yes.
Sir, my name is Savita. I am studying 8th standard, sir. Sir, I ask one doubt, sir. What purpose Newton created the first law, second law, and third law, sir?
Where?
What purpose Newton created the first law, second law, third law, sir?
Not clear. Your question is not clear.
No, sir. He is asking what is the purpose of Newton's to create these three laws.
Newton to create these three laws. So he has
what is the purpose?
Purpose. Why Newton has given this law? Is not. So he has seen whatever the experiment we showed, that he has seen, that made him to write down the theorem of that, and then this thesis is proved. Then it has become a law. Okay. All these things are based on practical experiments which they do, and also what they see. He saw the apple falling, then he enunciated the law of gravity. No? Whether the apple is falling on the earth means some pull is there, that he called gravity. So then he made the law of gravity. Then he saw that motion, one fellow cycling, he himself went and cycled, and then he fell down because of the obstruction. Then he started thinking about a law, that's the first law. Like that, you know. So they see the experimentation, they see the practical things, and then make a law of that. So you can also see some practical thing and then make a law. You can do that. And then you have to prove that law in the open forum. That is what is required.
Thank you, sir.
Atish.
Sir, good evening, sir. Myself, Atish Webu from Sairam Matriculation, Madipakam. Sir, actually, my doubt is, can rocket travel without those three orbits? Like as you mentioned in the clips, Leo orbit, Geo orbit, and polar orbit. Without this orbit, can it travel, sir?
Yeah, it can escape. That's called escape rocket. Suppose this rocket, the satellite which goes to moon, you know, that is not in this orbit. There's a different orbit. So that is Earth escape rocket. The trajectories are there. We will talk about that. There's a Hoffman transfer. So many new things are there in trajectory, which we will see later. But your answer to your question is yes. You can go in different orbits also.
Okay, sir. Sir, I have another doubt, sir. Sir, actually, in previous session, you mentioned about the dark energy. Does it have negative charge, sir? Because it has something named as dark. So
No, dark because the whole universe is dark, which you don't see, but there is an energy. That's why it is called dark energy. But there is not a negative charge. It is a charge, full charge, which pushes all the galaxies, at a higher speed to expand, to expand the universe diameter.
okay, sir. Thank you, sir.
Thank you.
Sir, good afternoon, sir. I am T. Bhadrasan from St. Anne's Military High Secondary School, Block 20 Navy, sir.
Yeah.
Sir, my question is about in the session you shown on graph now, sir, how rocket is flying now, sir. I want to know what is my azimuth degree, sir.
Okay. Suppose you want to launch a big rocket from Sriharikota. Want to launch.
Okay, sir.
And when it is going, it should not go over a landmass of another country.
Okay, sir.
If it goes, why it should not go? If it breaks, it's some problem. The whole thing, if it falls on the people, people will die. So
Okay,
you
sir.
have to orient the rocket, the direction of the rocket. It should be safe to do that. The launch. That means it should be clear launch. The direction what we launch should be clear. Okay, that is what is we call is azimuth.
Okay, sir.
So when you do a launch, don't allow nobody to talk in between. Otherwise switch off. We are conducting a session, in between why people talk. So you mute. Only those who are asking question should unmute.
Sir, and one more doubt,
Okay,
sir.
no, I will let me complete your answer, your question. So the azimuth is one direction of the launch, and the direction should not hinder the safety should not be compromised. So you launch it like that. So from Sriharikota, when we launch, if you launch it in a particular direction, it may hit the Sri Lanka. So what we do, we launch it such a way that there's a clear sea view throughout 5,000 kilometers, nothing is there if you launch at 140 degree azimuth. So this is called azimuth. Azimuth is the angle at which you place the rocket direction, the ground trace of the rocket. Okay.
Okay, sir. And one more doubt. What is my liquid propulsion storage, sir?
What is the?
What does mean by liquid propulsion storage, sir?
What is rebellion storage?
No, sir. Liquid propulsion storage servicing facilities,
Propellant,
sir.
not propulsion. Propellant. Liquid
Okay,
propellant.
sir.
Propellant storage. Propellant is what? The fuel and oxidizer which we explained to you, no? That is the propellant.
Yes, sir.
You have to store it. The storage means a place where they are stored. There will be a huge cylinder
Okay,
where it
sir.
will be stored. Okay.
Okay, sir. And why they're using N2O4 and M1, sir?
N2O4 and MMH. UDMH and N2O4. One is oxidizer, another one is a fuel.
Okay, sir. Thank you, sir.
N2O4, what is there? Why it is called oxidizer? N2O4. These are useless people, they are talking. The N2O4, there is a why it is called oxidizer? Hello, you answer. N2O4, you said,
Yes, sir.
Why it is called oxidizer? Not able to answer. Which class, which standard you are?
Sir, from 11th standard, sir.
Then you are not able to answer. You study chemistry?
Yes, sir.
Okay. N2O4. O is what?
O is oxygen, sir.
That is why it's called oxidizer. It has got oxygen. When you
Okay,
say
sir.
MMH, there is no O there. There is
Okay,
only
sir.
hydrogen is there.
Okay, sir.
So that is CH. This is O.
Okay,
That is
sir.
one is called oxidizer, another one is called fuel. Okay. So both together it is called propellant.
Okay, sir. Thank you, sir.
Okay, thank you.
Sir, good evening, sir. My name is R. Sanjeev Kumar and I am from Velamal Vidyas from Surapet, sir.
Okay, yeah.
Sir, my question is that why were the sounding rockets were named that way, sir?
Rohini, see, these are liking by the boss. Vikram Sarabhai liked Rohini. Why he liked Rohini? It is very close to the moon. That is a star. Rohini is a star, no? Close
Yes,
to the moon, it shows near to the moon. So he thought that we should name after the star. That's why he said Rohini. So there is no other reason. He liked that Rohini.
Okay, sir. And why were sounding rockets named as sounding rockets, sir?
Sounding means, you are not deliberately taking out a payload. It goes to an altitude and it is measuring the data. So it has got a measurement system and it is measuring that. That's why we call it sounding. Sounding means it's not making sound. That is not the meaning. Sounding means it's a rocket which is used only to do measurements.
Okay. Sir,
Sir, good evening.
Yes.
Good evening, sir. My name is Nirmanya. I am from Srimati Sundaravali Memorial School, New Perangalatur. You showed that experimental demonstration videos, sir, right?
Yes.
I just want to confirm about the active stabilization of the rockets based on my understanding. So when the rockets fly and change their trajectory, the engine swing to the opposite direction and correct their trajectory, right, sir? So, sir, thank you, sir. And I have one more doubt, sir. In the last class, when you talked about matter, there is a type of matter known as neutrinos, you said, right, sir? What is neutrinos, sir?
It's a particle. When you say different particles are there, so neutrino is one particle.
How it is different from other types of matter, other matter, regular matter?
There are, when you say particle physics, if you see, they talk about various particles in a matter, different particles. So this neutrino is one, it has got a character which can go at a speed of light, a neutrino. So in the universe, if you see, there's large neutrinos. It has got large neutrinos. When I showed you the universe, what it contains, when I explained to you, you have seen that 0.3% of the universe is consisting of neutrino.
Yes.
That's a particle. So that's why that we talked about particle physics. We talked about the strings and all those things. This neutrino plays a very important role in that. It's a particle. It's named after some scientist who has done that experiment.
Okay, sir. Thank you, sir.
So who is the scientist who has done that one?
I don't know, sir.
You heard about Bose? Bose. You heard about Bose?
Satyendra Bose, sir.
Bose has done the experiment with Einstein in the lab at Zurich, ETH, and he talked about the various particles. So that's why when the neutrino was found, and it was that whole experiment was named after Bose-Hassan. Bose and another scientist who got the Nobel Prize.
Okay, sir. Thank you, sir.
Okay.
Good evening, sir. I am Adithan.
From Sairam Matriculation School, Tirupati. Sir, how did the idea of flying machines evolve into the real rockets that escape Earth's gravity?
Flying machine, how the flying machine concept came?
What, sir?
You ask slowly. Important thing you are rushing. Okay.
Sir,
How?
How did the idea of flying machines evolve into real rockets that escape Earth's gravity?
See, you are talking about the flying machine means what? Flying machine is aeroplane is a flying machine, right?
Sir, like rockets.
Rocket, aeroplane, everything is flying,
Yeah, yes, sir.
Yeah, the concept came from, initially the concept came from the Wright brothers, who have demonstrated that we can fly. The Wright brothers.
Yes.
So then the idea of rocket came from Konstantin Przewalski, who said that definitely there will be a rocket and man can go into the rocket, and that is a flying machine he has found out, which I explained
Okay.
already. Whatever I explained, you are asking.
Okay, sir. Okay. Thank you.
See, another question came, which part of the rocket is doing the action reaction? This is not a correct question. What we are explaining to you, when there is a certain burn is taking place, that is a chemical burn, the chemical, when it is coming out from the nozzle, it is giving a force, pushing down the force. So the reaction is called the thrust, which is pushing up. There is no particle or no place. There is a definite place in the rocket which is called action reaction. It is not like that. Action is the exhaust which is coming out because of the chemical reaction and the chemical because of the burning of the propellant. Reaction is the pushing up, the thrust is pushing it up. So that is the Newton's third law.
Sir, good evening, sir. I'm from Saira Matriculation Higher Secondary School, Chennai. I have the doubt that how they thought by putting the gunpowder in the rocket, the rocket can fly in the starting itself. How the idea came?
How the idea came? So when the Chinese, when they started burning the gunpowder, they have seen it burns. Then they put it in a small bamboo stick and then put it there and use that and fire that the gunpowder. They have seen that the bamboo stick was going up. So then they thought, why not we use it in an arrow to make the arrow to go faster. So now the idea came from Indians. If you can do that, if you can channelize the flow through a nozzle, then the uniformity will come, which will enable the rocket to go up in a steered direction. So that is how the idea came.
I have one more doubt, sir, from previous session. We are so developed and so just a genius generation we are just going on. We found telescopes, sir. Instead of telescope, why we are not creating another like telescope and also why a telescope is very important?
Because you can see a long distance. Your eye has got a limitation. So the first telescope came from Galileo, who has showed to the people by adjusting the that optics, making it, we can see the long distance, we can see the stars, we can see the Uranus, all those things he told the people. So the telescope idea came from him, and then now we thought we should have a system by which we can measure at a long distance. That is why many different telescopes came. The Hubble telescope was one of the best telescopes, which was able to see the movement of the galaxies. So that is how we have now understood the universe.
Thank you, sir.
Sir, good evening, sir. I am Prajwal Sanjeev, studying in grade 8B from Wales Global School, Mogapet, Chennai, sir. From Wales Global School, Mogapet, Chennai, sir.
Okay.
Sir, the first satellite program of India was Aryabhatta or Rohini, sir.
Aryabhatta is a satellite.
Sir, which was the first, sir?
Which is the?
First.
First satellite is Aryabhatta.
Sir, then Rohini, sir.
No. First satellite launched by India using a Russian launch vehicle.
Okay, sir.
Using a Russian launch vehicle, we launched the Aryabhatta. That is in 74. Now 74, 75, that period. Now we have put the Rohini satellite is our own satellite and launched by our own launch vehicle, SLV-3.
Okay, sir.
That is why it is important.
Okay, sir. Sir, I have another doubt, sir. Sir, how does the stages of the rocket separate correct in the correct time, sir?
There's a timing. So you have got the rocket first stage, it burns. It has got a propellant, it burns. The burning is over. Now it has increased the velocity to some extent. Now it has to separate. There's a separation system which will cut the rocket. That part, burnt part will be cut. That is called a separation system. When we study the rocket systems in detail, I will explain to you. There's a thing called separation. So that separates the burnt stage and then give a push to the next stage. So what we do is we start the ignition of the second stage and then we separate so that it goes faster and the one which is separated goes down and finally it will fall down. In a trajectory, it will fall down.
Sir, then the part which is fallen down, where does the ball fall, sir?
No, it is a trajectory is there. You have got you throw a stone, you throw. That throw you after the force is over, the stone moves down, no? The parabolic trajectory, parabolic. Okay. So
No,
it
sir.
goes in the parabolic trajectory. Study mathematics, parabolic. Okay.
Okay, sir.
Next question.
Thank you, sir.
Who is next?
Sir.
Yes.
Good evening, sir. I am Akhil Batra, studying 11th standard in Javaga CBSE, sir. Sir, what is the difference between a satellite and a space station, sir?
Satellite, it has got a purpose. Purpose is communication or taking a photograph of the Earth or doing the GPS positioning. All these things it has got a definite purpose and definite, orbit, which are higher orbits. Polar satellite will be going in a 500-kilometer orbit, but whereas the communication satellite will be going in 36,000-kilometer orbit. That is called geostationary orbit. So different orbits are there. But when you talk about a space station, inside the space station is the zero gravity. It is a place where people can go, stay, and this. So it is a manned missions are called space stations, where the human being is there. They go orbit around the Earth. They do various experiments from the station. That is called space station. It is there for many, many, many years. For example, 25 years, International Space Station has completed. So that is what. But satellites are not living for a long time. Different satellites, 2 years, 3 years, or 10 years like that. That has got a different lifetime. So space station is the one which is there. It's a huge one. Space station is a huge one, 400 ton, whereas satellite is less than 1 ton, whereas space station is 420 tons. So that's the difference. Is it clear to you?
Yes, sir. I have another doubt, sir. During the space race, did any one of the superpower build a space station, sir?
From the repeat.
Did any one of the superpower has built a space station, sir?
Space station, many people have built. Russia built the first station long back. Mir station was there, and they have made a number of stations. But now International Space Station is a common station for all countries together. They have joined together to make it. America and Russia, they contributed for making the International Space Station.
Okay, sir. Thank you, sir.
Thank you.
Hello, sir.
Yes.
Sir, am I audible?
Very, very feeble. You are not taken.
Sir, am I audible?
Yes.
Sir,
Question.
myself, Philamadi of St. Anthony's Matriculation Higher Secondary School, Neyveli, sir. So my question is, how the scientists are estimating the direction of the rocket, sir?
Estimating the direction of the rocket. There is
Yes,
a
sir.
trajectory, we plan, suppose you have to put the satellite in a particular orbit, you have to design the trajectory to reach that orbit. So it has got different stages, where each stage builds velocity and how it will be taking each one to a place where it gives the ultimate velocity to put the satellite in the orbit. So that is the direction. The direction is called trajectory. You have to design the trajectory. For each launch vehicle, you have to design the trajectory.
Okay, sir. Sir, and then what is the purpose of the Kangayan mission, sir?
What mission?
Kangayan mission. Kangayan mission.
Gaganyaan mission. Gaganyaan.
Gaganyaan, sorry, sir, sorry.
Gaganyaan is manned mission. What is the
Oh,
mission? To put the people in the space. Indians also should go to space,
yes,
That is
sir.
called Gaganyaan mission. Manned mission. Simply in English, it is manned mission.
What is the purpose of that, sir?
That is, you have to go to the orbit for what? To see the Earth from there. That is number one. Second thing, you have to go to the space station. If you have to go in the, unless you travel to the space, you cannot reach the space station. That the space station is required for zero G condition experiments. It will give you a lot of information. Then you want to travel to Mars, you travel to other places. Everything is manned space mission. So unless you understand what is manned space mission, you will not be able to do later big missions. You want to land on the moon. That is manned space mission. The
Yes,
Americans
sir.
have done more than 50 years before, no? That is,
Yes, sir.
that is called manned space mission. Purpose is to reach the moon. No? They have
Yes, sir.
done it. So that's the
Yes.
purpose.
Okay, sir. Thank you, sir.
Good evening, sir.
Good evening.
My name is R. Ananta Padmanabhan from Jawahar Higher Secondary School, CBSE, Neyveli, Tamil Nadu. Sir, considering Newton's third law remains the core principle behind all rockets, how have modern technologies like ion propulsion or plasma thrusters challenged or extended this principle in space mission?
See, everything is same principle only. When you do ion propulsion or plasma propulsion, everything is called propulsion. Propulsion is to give you a propellant force. It gives a force. If you give a force, the reaction is the thrust. So same principle, but different propulsions. We have got solid, liquid, hybrid, cryogenic, ramjet. So many things are there. All are called propulsion. We will study that later.
Sir, I have another question, sir. How do the principles behind solid fuel rockets differ in practice compared to cryogenic or hybrid engines? And what are their advantages in modern launch systems like GSLV or LBM-3, sir?
So we want to know now. Now we have got different classes are there. I have told you last time that we are going to discuss about the principle. Then we are going to see what is the rocket. Then we will see the rocket systems. We will see under the rocket system, propulsion, control, guidance, electronics, satellites, everything will be studying. You don't jump. Huh? You wait. Wait. It will be discussed.
Sir,
Oh, yes.
am I audible, sir?
You ask the question. Unnecessarily you are
Sir, my name is Wilson David. I am doing grade 8 in St. Anthony's Matriculation High Secondary School. Sir, what is the difference between GSLV and PSLV?
So you did not listen to me? Did you listen to me when I explained what is PSLV, what is its orbit, then GSLV, what satellite is put in different orbit? I explained to you, You slept for some time?
No, sir, no, sir.
That I explained already.
Okay,
PSLV puts a satellite in polar orbit. GSLV puts a satellite in geostationary orbit.
Okay, sir.
PSLV polar orbit is for monitoring the Earth. That is called remote sensing satellite. GSLV puts a satellite in geostationary orbit for communication, focusing on only one place on the Earth. That is our Indian satellite, looks at India only.
Okay, sir.
Okay. Don't sleep, huh? The class.
Thank you, sir.
Good evening,
Good
sir.
evening, sir.
Yes. Kashta.
Sir, now I am audible, sir. Sir, my question is about how the satellite will work, sir.
We will see in the satellite class.
Okay, sir. How the rocket will follow the orbit, the three orbit, geo orbit, polar orbit.
We'll trajectory design, we will see how to put that in that orbit.
Okay, sir. Thank you, sir.
Thank you.
Good evening, sir.
Ah.
I'm Agathiar, studying 10th standard. I'm from Pillai Girls High Secondary School. Question is, why some rockets did not have a booster?
All the rockets have got a booster. Booster means strap on, you are saying? So some we do strap we do to give large force. What is the principle of rocket? Thrust divided by weight. You take thrust is T, weight is the weight of the rocket, right? If the thrust is equal to weight, what will happen? The rocket will stay there. If thrust is less than the weight, rocket will not go. If the thrust is more than the weight, then only the rocket will go up. Is it correct?
Yes, sir.
So you need more thrust to be given, more than the weight. If you give more, say 2 times, if you give, then the rocket will go faster. That is it will go faster. So all designs are made based on the requirement of the trajectory, how it should go. So sometimes we may put 1.2 times or 1.5 times, sometimes 2 times, sometimes we can 10 times we put it some rockets. So this depends on the design. So you have to have always the thrust should be more than the weight. Suppose a rocket is so big and you have to give thrust, big thrust if you have to give, and the center core is only a small liquid engine, it will not give that thrust. So you have to put a big solid rockets you have to put, which will give the larger thrust to take it up. That's why the rockets have got. So some rockets, what you are saying, their strap-ons are not there. The core itself will be able to give the required thrust. For example, SLV3, you have seen the SLV3 is a single booster only. So the booster gives a thrust of nearly 60 tons thrust it gives, but the weight of the rocket is only 17 tons. So it gives a good thrust. Depends on that.
Okay, sir. And I have another question. When rocket is launched, how we track the velocity of the rocket?
See, measurement. See, you have got different sensors are there. The rocket, different sensors. What are the sensors? You have got an accelerometer, which measures the acceleration. It has got a gyro, which gives the position. So all these things are computed. Position, acceleration, then compute the velocity. All these things are made based on the instrumentation we have got. So in a rocket, if you see, there will be something like 500, 600 instruments will be there, which will give you the measurement. And the whole thing is telemetered. When it is going up, there's a telemetry system to which all the information goes, and the telemetry communicates to the earth. That's how the information comes to us. So then we match with that. You have seen the graph, the velocity graph you have seen, and it is going exactly on the path it is going, what you have seen. So that is coming real time from the rocket only. Is calculated and then it is putting to the computer. Computer shows the plot.
Thank you, sir.
Thank you. Louder, louder.
How does a rocket move forward in space when there is no atmosphere?
When there is no atmosphere. Atmosphere has no meaning here. When rocket doesn't need atmosphere. It's burning inside, no? It has got oxygen inside. The fuel and oxidizer, which I told you. So oxygen is inside. There's no need to get oxygen from outside. So the rocket burns. Solid rocket has got ammonium perchlorate, which gives the oxygen. liquid propellant has got, we have got the N2O4, that is oxygen. So oxygen is inside. There's nothing to be obtained from outside. So it goes up. It burns. Okay.
How do scientists use type of fuel is for rockets?
How you would not see you? Be louder.
How do scientists use this type of fuel is for rockets?
I'm not hearing you. Harini, who is Harini? Harini, please. I'm going to close down now. Quick, quick. Harini.
Okay.
Mugilia.
Hi, sir. I'm E. Mugila from UAC Pillai Matriculation Higher Secondary School in Erode, studying 9th standard.
Very good.
I have a question. Do Newton's laws still work at very high speeds, like close to the speed of light?
Speed is not the important thing here.
Okay, sir.
The law does not talk about the speed. Law talks about only the principle. When action and reaction, when you say, if you are going in you are generating a speed of light, if you are that much velocity, if you can create, then rocket will go in that speed. No problem. No problem. It's only principle. It's applicable to any speed.
Okay, sir. Thank you very much, sir.
Sir, good evening, sir.
Yes.
Sir, I'm Harini from St. John's Metric School, sir, from Madurai, sir. Sir, I have a doubt on why isn't the rocket's nose extremely pointy? That would reduce the air resistance, right, sir? That would provide more speed for the rocket to move, right, sir?
No, it is the cone, what you are saying is called the heat shield. It's a shield to protect the satellite. And it is designed such a way that it is not going to give any problem. So it's a design. You see the cone, what you see a cone like the thing is not a sharp cone. It is designed with a curve at the top. So that is only to protect the the satellite. So once the dynamic pressure, that upper pressure is not acting, it is reducing, then what we do, that the satellite will be safe. Then we separate that. The heat shield is separated, and afterwards there's no shape. It is a satellite is up. There's no cone, nothing. We have crossed the atmosphere.
Okay, sir.
Okay.
Sir, another doubt, sir.
My name is Agathiar Shasta from Guntur Subaya Pillai, T. Nagar Girls High Secondary School, sir. How did Vikram Sarabhai found that magnetic equator passes through the Tumba village, sir?
That everybody knows about it except you. So he has gone there. No? We don't know where is the magnetic equator, but everybody knows about it. You see, Earth has got a magnetic equator. So it is going through that place. So he thought he should go there. How did he find out? Means it is there in the map, it is there. Earth equator map, it is there.
Sir, I have another doubt, sir. The smoke from rocket is making environment pollute or not, sir?
It goes quickly, it goes up, and it is from a remote place we do the rocket launching. It goes quickly, and it is from the seashore. So there is no pollution it creates in that place.
Okay, sir. Thank you, sir.
Come back to your car, no? You are having a car. That car makes more pollution than the rocket.
Okay, sir.
Sir, my name is...
Only 2 more questions. I have got another meeting.
Sir, can I ask doubt, sir?
Yes.
Sir, my name is Sheikh Adil from 9th standard Velamal Metric, sir. So before you said that rockets need to be balanced by stabilization during their flight in Earth, sir, because of the any unbalanced force in the atmosphere. But when they go to space, there is no longer an atmosphere. So is stabilization needed, or will they just continue on the needed path, sir?
Very good question you asked. See, stabilization, when we say, it is the center of mass and center of pressure. You have seen that? The experiment you have seen, no?
Yes, sir. Yes, sir.
Whether it is atmosphere or above, the same pressure and weight is operating. It is nothing to do with the atmosphere. As long as it is in the atmosphere, the lift and the drag, that is only acting. But the weight and the, that force, they are acting everywhere. So everywhere you have to balance it. Suppose you put the CG before the center of pressure, it will be stable. We put the center of pressure before the CG, then the rocket will tumble. So this principle is same everywhere.
Okay. Thank you, sir.
Sir, myself, Kalai Selvan from Velamal Vidyashram School, sir. In that, you shown on video, no, sir. On that video, they are saying weight should be concentrated more towards the nose part of the rocket, sir. Here
Front.
only I have a conclusion.
Not nose, front of the pressure.
Yes, sir. But combustion chambers weight is much more than the payload, no, sir. Why, sir, this combustion chamber is kept in
No. You are not talking about the nose. I'm not talking about nose. Center of gravity. Center of gravity in a rocket is not near the nose. It is in the center, based on the weight distribution. Okay. The center of pressure should be below. In a rocket, when it is there, center of pressure should be at the bottom. Bottom means below the center of the CG. That's all the principle. So you maintain that. If you maintain that, stability will be there. If you don't maintain, stability will not be there. Then you have to make some extra force to make it stable. Unstable also you can fly, but you need to do the force compensation you have to do.
Sir, then weight should be more at the tail part only, sir. End part, I mean.
CG should be in front of the acting pressure.
Then combustion chambers weight is more.
Combustion chamber is the pressure acting there. Okay. So that means the center of pressure is down.
Oh, okay, sir.
Weight will be in the middle of that.
Yes.
Good evening.
Thank you, sir.
Okay, sir. Thank you so much. Today class is over. I am having another program. So I want to complete that. Now time is also 8 o'clock. So Google is there? Google? So
Yes, sir. Yes, sir.
You can summarize and then.
Sure, sir. Sure, sir. So again, good evening to all present here. So it's again, I guess we had a session 2 with our Dr. Pillai, sir. We had seen last week on the space, and today we have seen about rocket. So definitely there was a lot of question answer sessions also was happened with Pillai, sir, and many students would have missed the chances. But whoever raises the first, they'll be getting the opportunity. So you can make it that to happen tomorrow also. We have our session 3. So I thank our Pillai, sir, and the coordinators and the students for making the session wonderful. Thank you, sir.
Thank you. Thank you, Dr. Balmunan.
Thank you, sir. Thank you, sir. Thank you, sir. Vocal, you can also explain about the question sessions, so that how the people need a question. Yes.
Hello. Okay, to all the students, given four numbers for every school. I think many of the students have participated and they're given that. Few of the students who are not given the CBH 2565 is going to continue. We will remove you from the group. It will also to be added up. So this is an instruction. Again, we are saying we will remove it. And next week or sessions onwards, we only accept the people who are coming inside with the code, school code. Otherwise, we will not be able to allow you for any session of Pillai, sir. So please try to put that in your mind and try to keep the code number and your name so that we will know that which school you are coming from. Wallace, sir, anything you want to say?
No, the coordinators need to mark the attendance. If coordinator is not there, so students need to update it in the WhatsApp itself. That also need to be updated. So whoever doesn't have coordinator, you need to mark yourself as attended today, and the attendance should be marked on a regular basis in the attendance sheet. That also need to be updated. So please inform them.
No, okay. Then, we can, I think, Pavilion can close the meeting if anything not there.
Okay, we can close it. We can close it right away. So we can discuss it by tomorrow. Okay. Before starting itself, we will make it.
Okay, thank you.